Hi, I'm Farhana and welcome to this lesson on trigonometry rules. Today we're going to be doing revision of our rules and specifically we're going to be focusing on exam type questions. So let's begin. Okay, just to revise our concept map, we've learned all three rules and today we're going to be focusing on applications. Let's quickly revise our rules. The sine rule, can you remember what it is? Sine A over A equals to sine B over B, which equals to sine C over C. And we have the reciprocal version, which you should be quite familiar with. Okay, and when do you use the sine rule? You use the sine rule when you have one full pair and one half pair. So either angle side or side angle, but not the including angle. Okay. But remember, we've got to look for the ambiguous case of the sine rule. And remember, ambiguous case occurs when the set that's given, the full pair that's given, contains the smaller of the two sides. So because 6 is less than 10, it will be the ambiguous case. And remember, in this case, we can draw two different triangles with the same information. So this occurs when we have two sides at an angle. And like we said, that we have the shortest of the two sides given. Okay, our area rule, half AB sine C, half BC sine A, and half AC sine B. And you use the area rule when you have side, angle, side. Again, remember, we're looking for that V pattern. So a side, an included angle, and a side. When do you use the cosine rule? When you have two sides and an included angle. And again, remember, that's when you have that V pattern that we discussed earlier. Or you can use, so these are the three formulas that you will use in this case. A squared is equal to B squared plus C squared minus 2BC cos A. And I think you're familiar with the other two. You can also use the cosine rule. Remember, when we have three sides, we just adjust the formula slightly to make cos A the subject of the formula. And then we can use this to find whichever angle we need to find if we are given three sides. So let's remind ourselves again, this is a revision. So which rule do we use? We start off by asking the question, is the triangle right angled? If it is, then we ask, does it involve angles? If it does involve angles, then we go right into our grade 10 trig. So we use our ratios to solve the triangle. We use sine, cos, and tan. If it doesn't involve angles, then we've got to use theorem of Pythagoras. Right, so this was grade 10 work. Now we get to the grade 11 work. So if the triangle is not right angled, then we've got to ask, do you have one full pair, that means an angle, and its matching side, the side across from it? If you do, then that's the green light for sine rule. Okay, so one full pair means we can use the sine rule. So we can either we have angle side or side angle, remember not the included angle. But if we don't have one full pair, then we've got to use a different rule, we've got to use cos rule. And again cos rule, side angle side or side. Okay, so that was a quick recap of the rules. Let's get to our first example. Okay. Quadrilateral ABCD is drawn with AB and BC both equal to 10. So we've got an isosceles triangle there. And we're given AC is equal to 10 root 3. And they've given us the lengths of CD. And they've given us one angle, 74,47 degrees. Okay, and they want us first to calculate the value of B. So we're going to start with that question. They want us to calculate the size of B. So B lies in our triangle ABC. So we're probably going to be using this triangle here, ABC. And if you look again, we're given three sides in this triangle. And remember, when we have three sides, what does that remind us of? It means we can use the cos rule. Okay, so to calculate the size of B. Now remember, because we're going to be using cos rule, because we have side, we want to find B. Which means when we're writing an expression to find B, we need to start our equation with AC squared, with the side across from B. So we begin by writing it like this. We'll say AC squared equals. Now, we're going to use our V pattern, remember, to fill in the blanks. So AC squared is equal to 10 squared, that's that 10, and that 10 squared. Okay, and then we write both those sides in the bracket here, so it's 10 and 10 for representing both these sides. And because we've started off with AC, we have to end off with the cos of the angle across it, and the angle across AC is B, and remember that's what we're trying to find. We're trying to find AC. Sorry, just give me a second to erase. Okay, right, now we found AC squared. But remember, we're looking for B, so we've got to do a little bit of rearranging, okay? Okay, so we have, we've got to substitute AC squared, because that's the other known value we have. So we're going to substitute, AC was 10 root 3, so we substitute that in. So AC squared is equal to 10 squared plus 10 squared to 10 times 10. Okay, let's just do some algebra quickly. Okay, so our algebra, we're going to bring this onto the right-hand side, so we end up with that, and then we just take this onto the right-hand side. Sorry, we brought the cos B onto the left-hand side, and we've taken this expression onto the left-hand side, right-hand side. Okay, sorry about that. Okay, and now we're just going to divide by that, because we're looking for cos B. We want to isolate the cos B, so we isolate the cos B, and we divide by 2 times 10. Put this answer into our calculator, and we're going to end up with cos of B equals to minus 0,5. Remember again that we are looking for B, so we've got to use our calculator. So we've got to take this 0,5, so we're going to say shift cos, and we've got minus 0,5, and we're going to find an answer, and the answer for B is now going to be 120. So B is equal to 120, and we've solved our problem. Okay, so the second question they ask us is ABCD a cyclic quad? So they want us to prove that ABCD is a cyclic quad. Okay, remember earlier we proved that B is equal to 120 degrees. So in order to prove that ABCD is a cyclic quad, in this case, if we can find the value of D and show that B plus D equals to 180 degrees, then we know that we've now proved that it's a cyclic quad, because this will mean that the opposite angles of the cyclic quad are supplementary. So we're going to begin by looking at triangle ACD and try and find the value of D. Now if we examine triangle ACD, we have one full pair, and we can work out D using this half pair here. So we're going to begin by saying sine of D over the side across it, and the side across that is 10 root of 3, is equal to sine of the angle, and the angle we are given here is this angle here, and we're going to use the side across it, and the side across it is 19,27. Okay, rearranging slightly so we can do the algebra. We're going to get 10 root 3 times sine 74,47 divided by our denominator. We're going to put this whole expression into the calculator, which is pretty simple. Your calculator will give you an answer of 0,866. Remember, you can't round off at this point. You've got to keep this answer in memory. And now because we're finding sine of D, we now need to use our shift sine value, shift on our calculator to find the value for D itself. And if we find D is 60, because remember that's what we're looking for, then we know we have a cyclic quad. Okay, so if you click shift sine D, we end up with D being roughly about 59,9, which is approximately 60 degrees if we round it off to the nearest decimal, which means now B plus D is equal to 180 degrees, and that means we've now proved that ABCD is a cyclic quad, because now we've just proved that the opposite angles are indeed supplementary. Okay, that brings us to the end of this session. We're going for a quick ad break. I'll see you after this. welcome back. So before the break, we were revising our trigonometry rules using some exam type questions. Let's continue with that. Okay, in this example, they've given us ABCD is a cyclic quad, and DC is 6 units, AD is 10 units, and D equals to 100 units, 100 degrees. And they've given us angle CAB, which is this little angle here, is 40 degrees. Okay, and in this example, we've usually been working through 2 decimal places. We're going to be working through 1 decimal places. They want us to find the answers correct to 1 decimal place. So they want us to find the length of BC, and they want us to find the area of ABC. When we're given an example like this, so we know we're doing trigonometry, but suddenly we see a circle. So we got to remember our circle geometry. So that's a clue that we're probably going to use some kind of circle geometry. And because we have a cyclic quad here, you have to remember some of the rules for cyclic quads. So what can you remember about cyclic quads from geometry? 2 important things we've got to remember. The first one is that opposite angles of a cyclic quad are supplementary, which is probably what we're going to end up using here. The other thing that we could possibly use, not in this case though, but is that the exterior angle of a cyclic quad is equal to the interior opposite angle. Let's see how we're going to use that information of geometry to solve this trig problem. Okay, so we need to find the length of BC. Now, again, we're going to examine our triangles. Remember, if it's a non-right angle triangle, we need 3 bits of information to solve it. So if we look at triangle ADC, we've got 3 bits of information. We've got 2 sides and an included angle. So we kind of have a V pattern here. And remember, if we have a V pattern, side, angle, side, we probably can use the cos rule. But we are being asked to find something in this triangle. We want to find the value of BC. But in this triangle, we have only 1 bit of information. We've only got this 40 degrees, which means somehow we need to find 2 other bits of information. So clearly we can see if we find AC, we've got 1 more piece to this puzzle of this triangle here. But clearly we need to find something else beside it. So it's easy, we could use AC. To find AC, we could use the cos rule. We understand that, we could use the cos rule in ADC. But what's the other bit of information we need to find? Again, remember I told you, why did they put this quadrilateral in a circle? Because they expect us to use Euclidean geometry to solve it. So remember, this angle is 100. So already we know we can find the value of B, can't we? Because those 2 angles, B and D, need to be supplementary. Okay, so first let's find AC squared. So AC squared is equal to, remember we're going to use our sides, so it's going to be 10 squared, right? So it's that side. And then this side, so 6 squared minus 2 times 10 times 6 times cos of the angle in between, which is 100 degrees. Okay, so if we put that into the calculator, we're going to end up with AC squared being 156,83778 and continuing like that. Again, remember, we cannot round off at this point because we need to get to the final answer. They wanted us to find the length of BC, so we've got to keep all this in our calculator's memory because we need to use this unrounded answer in the next step. So AC will be about 12,5 units. We need to find BC, because they did say we could round it off to 1 unit. We need to find BC, we can use our second triangle, and we already said that the angle B has to be supplementary, so we know B, because that was 100 degrees, B will now just be 80 degrees because it's the opposite angle of a cyclic quad, because together we needed them to be 180 degrees. Okay, so now we're going to use the sine rule in triangle ABC because it's exactly what we were trying to do. Okay, so now remember we want to find BC and we're going to use the sine of the angle across it, so sine of 40. And then because we have AC, it's what we found earlier here, we're going to say AC over the sine of the angle across it. And what did we say was the angle across from C? It was 80 degrees. Okay, we've got to do a bit of rearranging to try and get our answer. So we're going to say BC equal over sine 40 equals AC over sine 80. And remember, you have this answer in your calculator's memory still. So when you're doing this calculation, put it in, and then you're going to get a value for BC. Once you put this into your calculator, 12.5 times sine of 40 over sine of 80, and you should end up with BC is equal to 8,2 units. Okay, so that question has now been answered. Let's go to the next question. Okay, they want us to find the area of ABC. So to find the area of ABC, remember already we've got an expression for AC. Okay, we found AC earlier, and we found BC. Okay, and we found that this angle was 80. Okay, so if we want to use area rule, we want to try and use this V pattern, which means we need to find this angle. Then we have side, angle, side. Remember, for area rule, you need side, angle, side. So we've got two sides. Because we have the other two angles, we can find the included angle. So we can find that angle quite easily by just subtracting the other two from 180 degrees. So let's do that calculation quickly. So angle ACB will equal to 180 degrees minus 40 degrees minus 80 degrees, and we're going to end up with it being 60 degrees. Okay, and that's just by doing the sum of angles in triangle ABC. Okay, now to plug in our values into our area rule. Remember, area is equal to half AC times BC. So it was AC, okay, times BC times sine of the angle in between, and the angle in between we just found to be sine of 60 degrees. Okay, so plugging in now values. Earlier we found AC to be 12.5. We found BC to be 8.2 earlier. And so we plug in those values that we found earlier. All that's left to do is put this into our calculator, which is pretty straightforward. And look at the answer that we're given. And remember, it's our units squared. So our answer is 44,4 units squared. And that's the value for our area of our triangle ABC. Okay, let's go to our next example. In this example, we've got a triangular park, and we've got represented by PQS. R is a point such that they've given us values for R is a point on a line SP such that QR divides the area of the park into two triangular parks. PQ is equal to PR, which is equal to X. So those two are both X, meaning those two lines are equal. Remember, if those two lines are equal, we have an isosceles triangle making that angle equal to that angle. Okay, they give us the value for RS, and they give us the value for RQ being √3 X units, so that one. Okay, and they want us to calculate first the size of P and then the area of the triangle QRS in terms of X. Okay, so because they want us to calculate the size of P, you will notice that in this triangle, we've given 3 sides. We've got 1, 2, 3 sides. So we're going to use the cos rule to find the size of P. And how do we do that? Because we want to find the size of P, we're going to start off with the side across it when we're writing the cos rule. So we're going to start off by saying QR squared. So when we begin our cos rule, we're going to say QR squared, so that one, equals, and we're going to use now the other 2 side squares in our cos rule formula. So it's going to be X squared plus X squared. So it's going to be, it's going to be PQ squared plus PR squared minus 2PQPR. And remember, because we started off with QR, we're going to end off with the angle across from QR, P, because that's what we want to find. Now what's left is to just substitute the actual values that we have or the variables that we have. So we're going to end up doing that. So QR squared is going to be √3 X squared. PQ squared is going to be X squared, X squared. We're going to put an X in there, we're going to put an X in there, and remember we want to find P. Okay, we're going to do a bit of algebra now quickly. So we're going to basically take this 2x, this becomes x squared. We're going to take it onto this side, so it'll become positive 2x squared cos P and we're going to take this expression, square it out, and take it onto that side. Okay, we just clean up some algebra here, because remember we want to solve for cos of p, so it means I got to get rid of this 2x squared. I put the 2x squared into the denominator, and now we have an expression for cos of p, but remember I want to clean it up a bit still, so I want to do some algebra, and I notice I have some like terms here, so I can add the terms. Okay, and if you notice that you're going to have x squared plus x squared, and if you did the algebra on minus root of 3 squared, you're going to end up with 3. Okay, so you ended up with x squared plus x squared minus 3x squared, and that's how we ended up with minus x squared in the numerator here. And our denominator was 2x squared, and now we can just cancel out the x squared, so we're going to end up with cos of p equals to negative a half. Now remember, they wanted us to find the size of p, so we need to use our calculator and use the shift button. So we're going to say shift cos of negative a half, and the answer that we'll get is 120 degrees. So it means that this angle here is now 120 degrees. Okay, one more question on this. They've asked us to find the area of the triangle QRS in terms of x. So we need to find the area of this triangle here, QRS, in terms of x. And if you notice already, we've got one side and we've got two sides, so we're going to try and make a plane to get some other information. Okay, so we're going to be finding, earlier we found out that this was 120 degrees. So because that's 120 degrees, if I wanted to find these angles, because remember we said they were equal, I had to say 180 degrees minus 120 divided by 2, and I would find out that each of these angles, Q2 and R2, is simply 30 degrees. And how do we know they're 30 degrees? Because of angles, sum of angles of a triangle. Okay, that's pretty standard grade 9 work. Okay, remember we're finding the area, so we've got to find this angle here. We were looking for this angle here. So how do we find R1? Because it's adjacent supplementary angles, we just subtract 30 from it. Okay, so our area of QRS is going to be half QR times RS times sine of R1. And remember, we just got to substitute the values in, substituting the values in for QR and RS. And remember, we found R1 to be 150. Just clean up some of the algebra. And we're going to end up with, if we put it into our calculator, we're going to end up with 0.6495 x squared. So roughly, our area for our triangle QRS is going to be 0.65 x squared. Hi, welcome back. So before the break, we were dealing with trigonometry rules and some exam type questions. Let's carry on with that. So this example says, in the diagram DCB equals alpha, AC equals to h units, they want us to find the size of ACD in terms of theta and alpha, and then there's a few other questions, we'll get to that in a minute. Let's begin with the first question. Finding the size of ACD in terms of theta and alpha. Okay, so they want us to find the size of this angle, C1, this little piece here. So because the whole angle is theta here, and the small piece here is alpha, so obviously ACD has to be just theta minus alpha. You'll often find that they ask you to name angles like this. So you'll give you a bigger angle and a smaller angle, both variables, and you have to find one of the other angles. So this technique of realizing that this little angle here is going to be the bigger angle, theta minus alpha. It's quite important. Okay. The second question wants us to prove that AD equals H sine theta minus alpha over cos of alpha. So because we want to find AD, we're going to go to our drawing first and examine the drawing first. So let's go see what they ask us first. They want us to find AD. We're going to go look at both triangles and see what information we have. So if you go to the triangles and you look at the triangle, this triangle little at the bottom here, this BCD is a right angle triangle. We've got an angle and nothing else in the triangle. In triangle ADC, this triangle here on top, we notice that we have H. We've also been given, or we now have an expression for angle ACD, and they want us to calculate AD. So they want us to calculate AD. I have the angle across from it. Okay, I can try and find the value of this angle here in terms of alpha and theta. So we try and be busy. Remember, we're dealing with this triangle here. Okay, and we're finding AD. And we want to try and, because we have an expression for, we want to try and find this angle here in terms of our variable. Now, this angle also belongs to the big right angle triangle. And the big right angle triangle ABC, we've got A, B being 90, and we've got angle C being theta. So we've got three angles. We've got angle A, we've got theta, and we've got 90 degrees, which means A now has to be what? It's got to be the complement of theta. So A, this angle here on top, actually is 90 minus theta, using three angles of a triangle because the sum of angles of a triangle. Okay, so let's go put that into our sine rule. So we have AD over the sine of the angle across it. And remember, across from AD was C1. And C1, we found C1 to be, or ACD to be, theta minus alpha. Okay, and then the other pair, the full pair we're going to be using is this one and that one. So we're going to say H over the sine of the angle across from it. And the angle across from D1, from H is D1, but we need to find D1 in terms of the angles that we have. And if you notice that D1 is an exterior angle to this triangle here. So it's an exterior angle to this triangle here. So D1, we know that D1 has to equal to that angle plus this angle here. So it's 90 plus alpha. So again, in our sine rule, we're going to say AD over sine of C1 equals H over sine of D1. And D1 we said was 90 plus alpha. Okay, and remember this 90 plus alpha should already start reminding you of something. Because there's a 90 here, we're probably going to end up using the co-rule or the changing to the co-ratio of its complement. Okay, so remember again sine of 90, let me just change this color. So remember sine of 90 minus theta, we're going to change it to its co-ratio. So the co-ratio is cos, so it will become the co-ratio of its complement, so cos of alpha. Okay, and now we're going to find, they want us to find AD, so we're going to make AD the subject of the formula, which means we're going to multiply both sides by sine of theta minus alpha. And we're going to get H sine theta minus alpha equals to cos of alpha. And that's exactly what they asked us to prove. So we've proved that AD is equal to the expression that was asked for. Okay, they ask us to determine the length of AD correct to two decimal places. This is pretty simple because now they give us the actual values. This is just basic substitution, so you're just going to substitute the values in and get an answer with your calculator, 10,59 units. And now we have a value for AD, which is approximately 10,59 units. Okay, the last question is determine the area of ADC. So now we want to find the area of ADC. Remember, we've just found AD now, okay? So how are we going to find the area of ADC? We know that AD is 10,59 units, And we know that h is 17 units because they gave us earlier, right? In the C part of the question, they gave us the value for h. And this one here is 10,59. So if we can use side, angle, side like this, we can use area rule using those values. So if we're writing, they've given us also that theta is equal to 58 and alpha is equal to 23. So angle A, which was 90 minus alpha, must now be 90 minus theta must now be 90 minus 58, which is 32 degrees. Okay, so area of ADC will be half of 17 times 10,59 times sine of 32 degrees. Okay, putting that into our calculator, we're going to end up with area of ADC to be 47,70 units. So this was basically just substituting, this question was just substituting into whatever we found earlier. It should have been pretty simple then. Okay, so we've reached the end of this session. We're going for a quick ad break. I'll see you just after this. Hi, welcome back. So before the break, we were doing some exam type questions. We continue with our exam type questions. I hope this is getting a little bit easier for you. Let's go. In this example, they gave us that TRS is a secant of the circle and SU is a tangent at U. Furthermore, they give us that TU is equal to 16 centimeters, TR is 12 centimeters, and T is equal to 41 degrees. We asked to calculate the length of UR, the size of U2, and the length of TS. Before we begin, let's first examine our diagram and see what information is given and how we can use it. Okay, so we have three triangles. First of all, they've given us a circle, so that's an indication that we're probably going to use circle geometry. We'll discuss what in a second. Okay, so they've given us three triangles. We have this triangle where we've got side, angle, side, which means we can use cos rule. This triangle here, we have no information at the moment. So at the moment, there's nothing we can do with a triangle. And there's a bigger triangle, triangle TUS. In that triangle, we've got one angle 41 degrees and one side 16. We don't have US and we don't have TS. So as we get through the problem, we probably need to find some other information, either using trigonometry or possibly geometry. So because we have a tangent, we've got to remember our tangent theorems. One of the theorems we can remember from geometry is that radius is perpendicular to the tangent, but there's no radius given here, so we're probably not using that one. We do know the tan chord theorem, and because we have a tangent and a chord, we're probably going to use the tan chord theorem at some point. Let's see how that happens. Okay, first we're going to find UR correct to two decimal places. This is pretty simple. UR is in this triangle. We've got the V pattern across from it, so we know we're using cos rule. So that's pretty simple to write out. So UR squared is going to equal to, we can start with the first side squared, 16 squared, and then 12 squared. 2 times 16 times 12, and because we're dealing with UR, the angle across from UR is 41 degrees. So we've got to plonk that in. Okay, we're going to put that into our calculator. We're going to end up with UR squared equals to 110,19 degrees. Again, we want UR, so we're going to take the square root of this. Taking the square root of this, we'll get the answer to be 10,50 centimeters. Okay, so now we have a value for UR. UR is 10,5 centimeters. Right. The next question, they want us to calculate the size of U2. Remember, we calculated UR 10,5 centimeters. Now they want us to find this angle here. Okay, now remember, we've got this value here, 10,5. So in this triangle, we've got side, side, side. So we can use, because we have side, 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 we can use cos rule to find U2. And remember, because we're finding U2, we're going to start off our cos rule with the side that lies across from U2. And if you look at U2, the side that lies across from U2 is TR. So our expression is going to start off with TR squared. Okay, so we're going to write our cos rule out. Okay, so we're going to start up our cos rule with 12 squared because we wanted the side across from UR. Because we wanted to start with the side across from UR, because from U2, because we are calculating angle U2. Okay, so which other sides do we put in between? The other ones that we haven't used. So we're going to start off with 16, okay, and then 10,5, what we found earlier, and again 16 here, and again 10,5 in here. Okay, now remember again we're solving for U2, so we're going to have to do some algebra to make U2, the cos of U2 the subject of the equation. So we're just going to do a bit of algebraic manipulation here, bring that onto this side, take everything else onto that side, and now we're going to divide by whatever is not U2 because we're isolating the cos U2 part. We're going to put this expression into our calculator with shift cos. So once we put shift cos and this entire expression into our calculator, this expression becomes 127 over 192. That's from your calculator, and now you're going to find the inverse, shift cos of 127 over 192, and we'll get the answer of U2 being 48,59 units. So what we found, because we had three sides, we found this angle here. This angle, 48,59 degrees. Now, because this question continues, we're going to be needing this answer for the next part of the question. Okay, so now I've just put it into the diagram. That's what we just found. Okay, they want us to calculate the value of TS. So they want us to calculate the value of TS, that line there. Now, in order to find TS, it belongs to the big triangle. We're missing a couple of things, aren't we? So we have, in the big triangle, we've got this side. If we can find these angles in the big triangle, it'll really help us. So now remember again, we said we're going to use some kind of geometry here, and we can already see that this angle, U3, using geometry, has to equal to 41. And the reason for that is 10 chord theorem. So that's 41 degrees. Okay, now because we have the other two angles in this big triangle STU, it's quite easy for us now to find angle S. So let's write that down quickly. Okay, so we said U3 is equal to 41 because of 10 chord theorem. Okay, U2 plus U3 now together, these two together, will give us 89,59. We're going to use that now to find angle S. So angle S will equal to 180 minus 41 minus 48 minus that amount there. So S will equal to 49,41 degrees, just using the angle sum of a triangle. Now we're going to apply sine rule to this big triangle STU. So let's begin. Remember, we are looking for the length of TS. So because we're looking for the length of TS, we're going to start with TS, and then we're going to use the sine of the angle across it. And the sine of the angle across from TS is that angle there. So we're going to say sine of 89,59 degrees. So the other full pair we have in the big triangle, remember it's 16, and the angle across it. And the angle across it was the angle S that we just found now, which was 49,41. So it's going to be 16 over 49,41 degrees. Okay, now we're going to rearrange that to make TS the subject of the formula. So it will be 16 times sine of 89,59 degrees divided by sine of 49,41. Put that into our calculator, and we end up with TS being approximately 21,07 centimeters. Okay, our next example, we needed to show that ABCD is a trapezium. Sorry, they've given us ABCD is a trapezium. We've got parallel lines. AD is parallel to BC. DAB is 90. BCE is 150 degrees. CD is produced to E. F is a point on AD such that BFE is a straight line and CBE is alpha. So they've given us this is alpha. They've then given us the angle of elevation from E to A is theta. They've given us this side is x, BC is x, and they've given us CE is 18 minus 3x. Okay, they want us to calculate to find BE equal to AB, to show that BE is equal to AB cos theta of sine of alpha minus theta. So we're going to go and look and see where is BE, which triangle does BE fall in, and we're going to try and solve that. Okay, so we need to show that BE is equal to AB cos theta over sine of alpha minus theta. So we have some things we need to do, some kind of decide which triangle we're going to use to solve BE. So first we're going to try and look at what had they given us. They've given us parallel lines, and because they've given us parallel lines, this angle and this angle must be equal, which means this angle has to be alpha because it's corresponding. And because that angle is corresponding, we are trying to find something with BE. So we're probably going to look at BE in one of the triangles, but we need to find some other angles. We can also find the value of E1 in terms of alpha and beta, because if you notice, this angle is an exterior angle of this triangle. So alpha is the exterior angle. So in other words, I can find an expression for E1 using alpha and theta if I need. So remember we said F1 is equal to alpha because it's corresponding angles. Okay, and F1 is equal to theta plus E1. And so therefore E1 is equal to alpha minus theta. Now we're going to need that information when we continue with the example. Okay, so in triangle ABE, BE and the angle across it, so we're going to use sine rule. So BE and sine of the angle across it. Now remember this angle is 90 plus theta. So this angle is 90 plus theta, okay, equals to AB and the angle across it. And the angle across from AB is this angle here, so it's going to be alpha minus theta. Okay, because remember we're trying to find BE, so we're starting to find BE, and that's where we ended up. Okay, so we ended up there. BE is equal to sine of 90 plus theta, BE over sine of 90 plus theta equals to AB over sine of alpha minus theta. Remember again, this is going to remind us of our co-ratio rule, so we're going to have to change that in a second. Okay, so if I multiply both sides by sine of 90 plus theta, and the next step I'm going to change it to my co-ratio, sine of 90 plus theta becomes cos of theta. And now I have an expression for BE. And BE is equal to AB cos theta sine of alpha minus theta, as we needed. Okay, so the next thing is show that the area of BCE is equal to the expression on the right-hand side. Okay, so basically we want to find an expression for the area of BCE. Now if you notice in the triangle, in triangle BCE, we've got this to be x. We've got a value for this because this is 18 minus 3x. This length of EC here, so this one here. So we have that, and we have that, and we have the angle in between. So we're going to use that to write our area rule, which is pretty simple now. Area is equal to half x, so x times 18 minus 3x times sine of the angle in between, which is 150 degrees. We're going to put all the numbers and do some algebra and put it into our calculator. So sine of 150 is a half, and then put that into the calculator. Let's just first multiply half times a half. We get a quarter. And just doing some algebra, a quarter of 18 is 9 over 2, and a quarter times 3 will give us 3/4. So we end up with the area of triangle BCE is 9 over 2x minus 3, and then we've got x times x, so it's x squared over 4. So, have we answered the question? Yes, we did, because our expression matches the question that was asked. Okay, so that was a pretty intense session. We did a lot of work. I hope this helps you to understand how to approach an exam type question, and hopefully you'll have fun practicing from now on. Thank you for joining me. Bye.